See, suppose you have been given a vector that I am showing it here on the screen, and let me call this vector as AB. This vector is AB, its tail is A, the starting point, and the head or terminal point is B, right? And it's also given that the coordinates of the point A is given as x1, y1, z1. And the coordinates of the point B in space is given by x2. The numerical values, I'm just writing the symbolic form, x2, y2, z2. So once again, we have got a vector given by AB whose tail or initial points coordinates are x1, y1, z1, and the head or terminal points coordinates are x2, y2, z2 in a three-dimensional coordinate system. How can we express AB in terms of I, j, and k? That is the question. We can solve the question with the help of what we have learned so far on position vector. You see, I have constructed a coordinate system. This I'll be naming it, and let me name it first. Now this was the coordinate system, that is O, this is x, this is y, this is z. OXYZ coordinate system, that is, and in this coordinate system I have first found out a joined O to A, so this becomes, OA becomes the position vector of the point A, the initial point of the vector AB in question. Similarly, I have joined O to B, the terminal point, and that OB is standing for the position vector of the terminal point B of the vector AB here. So of course, in the triangle OAB, I could write down by applying triangle law that OA, you can see it two sides in the same order, that is OA plus AB must be equal to vectorially the third side in the reverse order, that is coming out to be OB here, right? So I could write down that AB vector, that is my question, that is the vector under investigation in green ink here. AB is given by OB minus OA. This is an interesting result itself. You can have a look at it. You see that any vector can be written to be the difference between the position vectors of the terminal point minus position vector of the initial point, like that. This is of course OB is my position vector of the point B, the terminal point, and similarly this is the position vector of the point A, the initial point, right? So I have got AB to be the difference of those RB minus RA. And again, we have learned little earlier that if I know the A's coordinates x1, y1, z1, we have known that OA could be written to be, that is actually position vector of the point A, and that is x1 I cap plus y1 j cap plus z1 k cap. This is thanks to my question number 1. If you remember, some time back we have done that any position vector of any particular point can be expressed as in terms of ijk in terms of its respective coordinates, like this. Similarly, I can go ahead and write down that the vector OB, that's position vector of the point B, the terminal point here of the vector AB, and its coordinates also given x2, y2, z2. So I could write down using question number 1 given before. I rather take it off here. I don't want to confuse you. You have got equation number 1 earlier, and this RB can be written to be x2 I cap plus y2 j cap plus z2 k cap. I am making use of this equation written earlier, that any vector R can be expressed to be xi plus yj plus zk if xyz are the coordinates of the point whose position vector is found out. I am making use of this one here, and I wrote correspondingly for the points A and B these two expressions OA and OB. And we just now found this is there, AB. I'll make use of this now, and I could write AB is coming out to be, since it is OB minus OA, I written already earlier, OB minus OA. You can make use of the previous two steps, OA and OB, and you are getting AB is coming out to be x2 minus x1 in bracket into I cap plus y2 minus y1 in bracket into j cap plus z2 minus z1 in bracket into k cap. What is the result? Once again have a look. Any vector whose initial point is x1, y1, z1 and terminal point is x2, y2, z2 could be expressed as x2 minus x1i plus y2 minus y1j plus z2 minus z1k, thanks to my application of triangle law, as we have shown here by drawing the position vectors of the points A and B on this vector AB. And that was an important corollary. We shall need and make use of that quite often. You can go further from here and write down that the length AB, as we have done earlier for equation number 2, that was, I remember we had given equation number 2 was square root of x square plus y square plus z square for any given point of coordinates x, y and z. This is equation number 2. If we make use of this, I could write further that the length AB, that is the magnitude of the vector AB, can be written to be x2 minus x1. Always keep in mind what quantities represent what, plus y2 minus y1 whole square plus z2 minus z1 whole square. Now that is the length of AB, as equation number 2 up there will corroborate. I am talking about this equation. The first one of course gave me the RA and RB, which we made use of to get AB by subtraction, vector subtraction here, and then we got the length of AB by making use of equation number 2, and this is the length of the vector arrow AB that you can confirm yourself.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.